Hello everyone, my name is IOcken, and I am enrolled in ECE 311, 331, and 341. Today I will show you and explain the power management system, which takes an AC input and converts it into a more DC-ish output, thus going from, say, a wall plug to a battery, and that is the power management system. We will start this off by talking about the diode, which is a combination of two semiconductors. One is a doped p-type and one is a doped n-type. P-type having positive carriers, n-type negative. And when you apply a voltage across this diode, it opens up what is called the depletion region, where ions form on either side, and this creates an electric field and current going the opposite direction, which creates work throughout the diode, and your voltage, electric field, and the power of the load, of the resistive load in the entire circuit diagram are all directly proportional. So one goes up, the rest of them go up. And when you analyze the entire diode bridge system, this gives, when you input just a sinusoidal V in, you get the absolute valued system of the sinusoid. And this system is nonlinear because it fails both homogeneity and additivity, because if you scaled your x by -1, you get the inverse sinusoid, and you still get the regular absolute valued sinusoid. And if you add x1 to x2, you get a 0 function as your output, and that is obviously not true because this is still just the absolute valued sinusoid. Let's take a look at Gauss's law and charge density in this diode, because same as before, you have your VD on going across, and then with these ions they create a positive charge density and a negative charge density from -D to D of the depletion region. And with this you can create a Gaussian surface from the positive charge piece over and past the negative charge piece, making the shoebox, as it is called. And from there we can analyze the electric field. So if you graph the electric field in accordance to the respective charge density, on the negative end it goes negatively, and you have this area, and then as you go to the positive side, it goes back up positively along x, because this is planar Gaussian, and your voltage is the integral of E, as we know, and you take that integral from -D to D, and thus you will get your VD on is equal to 2V out, or V out is 2 times V on, because you will have 2 diodes on at any given time. And this still gives us the absolute valued sinusoid, but we want a more steady DC source. So what can we use here? Let's take a look at the current is equal to instantaneous change of current over time, and if we integrate both sides here, we get Q equals C basically times instantaneous voltage, which we can use a capacitor to achieve this. And now, speaking of capacitor, let's look at the RC circuit component. In here, we can give it a step response as our Vn, and with this, we gain an infinite slope, basically, and we have our I equals C times dV over dt as before. But this slope, everything will go to infinity, your I and your dV over dt, therefore shorting the capacitor. And if we look at this from an impedance standpoint, we have 1 over JWC, and W, our omega value, is equal to 2 pi f, and this frequency is infinite at this point, thus not giving it open, but shorting the capacitor again. And if we look as the capacitor charges over time, as t goes to infinity, in this graph of your time constant, tau equals C times R, and that R is what is seen by the capacitor charges up, and at this value, say infinity, your current is 0, because the slope of this derivative at any point will be 0. And then we can apply another step response, this time different. It'll be shifted. We will have the same one as before and a T0 shifted one right here. So we take this step and we give it the initial step as we saw before, just infinite slope right at t equals 0, and then on. And then you have the inverted and delayed step that when you add these both together, they give you the charge and the delayed discharge after that initial charge, giving you the shark fin sinusoid over the voltage over R1 and R2 in the voltage divider. And if we look at this from a whole system standpoint, we now know that the capacitor will charge up and decrease and charge up over time, periodically, because this is a time invariant system. And we look at our Vin, which is the tallest graph here, and our Vrec mimics this Vin, but is below it because of the 2 VD on threshold. And then you look at your Vout, which has a difference of the voltage across this first resistor, and then this difference is actually time variant. Therefore, at the beginning when the diode turns on and crests, and then the capacitor starts to discharge, this one, because it varies with time, will actually merge, and your Vrec will equal your Vout as the capacitor discharges. And then it will repeat this process over time, and this gives us a more constant DC out voltage, which is great because this is a power management system, and we have our sinusoid being converted into a more DC output source through the diode bridge, which is 2VD on, which I don't know if I think I mentioned, it has to be less than Vin at all times, logically, because you can't have more than the source. And this whole system, both the rectifier and the RC circuit combined, give us what we want at our DC output. All right, I hope you all enjoyed this video, and I hope you understand what I was trying to convey, and I hope you all have a good night, and good luck on the rest of your video.